Hello, it's my pleasure to talk to you about the subject Augmenting the Actual with the Abstract, an austere application of artificial intelligence. But before I begin, I want to talk about real intelligence first. You know, we're celebrating today, or this month perhaps, the entire month, the 50th anniversary of Sandholm and Associates in Stockholm. And so Leonard Sandholm, who established the company 50 years ago, I take my hat off to you. I haven't even made 30 years in my consulting company, so to make 50 is indeed a very special milestone. And Lars, I believe that you have now been associated with the company for almost 25 years, almost half of the time that it has existed. And now as the president, you're carrying on the tradition of Sandholm Associates here in Sweden and abroad. So to both of you, I say, hearty congratulations from the bottom of my heart. Well, we're going to talk today about artificial intelligence. And what is it? So I want to begin with a little story. Back when I was in the United States Navy, we were talking about applying artificial intelligence in some anti-submarine warfare operations. And I was at a meeting with the Undersecretary of Defense. And I remember very distinctly when we were proposing artificial intelligence. And I remember exactly what he said to me, and even the tone of voice. So when I talked about artificial intelligence, he said, "Commander Watson," he said, "we don't have enough of the real thing. Why should we invest in this artificial stuff?" And we didn't go forward with that program. So what is artificial intelligence? Is it something of science fiction, like he was thinking back maybe in the 1970s? Or is it something whose time has come? The popularity of artificial intelligence actually began in the 1980s with what has in retrospect been called the AI winter. And what happened is there's a lot of issues about it, and then it just went as a cold topic not to be pursued because it didn't get practical. So let's think, first of all, what do we mean by artificial intelligence? You'll have to edit that little scratch out. It didn't look good. So, artificial intelligence, according to Oxford's online dictionary, is a theory and development of computer systems able to perform tasks that normally require human intelligence, such as visual perception, speech recognition, decision-making, and translation between languages. And so now, maybe you can think about when you're on the internet and you see something in a foreign language. Have you ever gone to a Google Translate function, perhaps, to understand what it means in your language? Well, of course, many of us have done this. And so we start seeing that artificial intelligence is actually coming into our everyday lives. So IBM defined artificial intelligence as it leverages computers and machines to mimic the problem-solving and and decision-making capabilities of the human mind. John McCarthy, who actually coined the term early on in 2004, defined artificial intelligence as the science and engineering of making intelligent machines, especially intelligent computer programs. It is related to the similar task of using computers to understand human intelligence, but artificial intelligence does not have to confine itself to methods that are biologically observable. In other words, it can create its own methods that go beyond what people do. Well, there's a history in its development. So let's begin back in 1936. Alan Turing, who's perhaps best known in science fiction and the movies as the creator of the computer that broke the Enigma code of the Germans during World War II. And in 1936, he defined a computable number as a number whose decimal value can be written into a machine. Now, his first machines were mechanical machines. That's what the Turing machine originally was that broke the code. It was a whole bunch of mechanical switches. But because it used numbers as digits in decimal, it could actually do the processing to break the cryptography problem. 1945, Vannevar Bush, who had been in charge of the scientific programs during the Second World War for the United States Office of Scientific Development. He made a comment, an article in the Atlantic Monthly called As We May Think. And in this, he described what would happen in the future if a machine system was able to amplify the way people gain knowledge to create understanding, where it's possible to collect and store knowledge inside a machine that was just like a piece of furniture in your house. Well, now many of us have workstations at home with computers sitting on desktops, a piece of furniture. We see it as a normal part of life. In 1950, Turing asked the question, can machines think? And this was a very important question. It was in Mind magazine, which is a journal about philosophy of science and analytic philosophy, linguistic philosophy. And in this article, he proposed what has become called a Turing test to demonstrate, is a machine capable of surpassing human intelligence? And this became the gold standard for understanding how smart these machines really have become. John McCarthy in 1955, who I quoted just earlier, coined the phrase artificial intelligence. And in 1966, the very first programs were written about it. Now, today, the most widely used textbook on artificial intelligence was first published in 2001 by Stuart Russell and Peter Norvig. It's now in its 4th edition. So basically, as a teachable subject in universities, it's not a very old topic. If we take a look at the history in more depth, we see that after we had coining the term in 55, we saw Alan Newell, J.C. Shaw, and Herbert Simon, who was a behavioral psychologist who wrote the book Administrative Behavior and won the Nobel Prize for creating behavioral economics, created the first AI software program that worked. It was called the Logic Theorist. In 1967, Frank Rosenblatt built a computer called Perceptron based on neural networks that were learned by trial and error. So that's the same way that Thomas Edison learned how to actually create a light bulb. In 1968, Marvin Minsky and Seymour Papert published a book called Perceptrons, which defined the state of the art. And this has actually been taken up in science fiction to talk about perceptrons as a type of being, if you will, in the future. 1980, adaptive learning using what's called backpropagation algorithms, or a part of neural network, was used to calculate loss gradients across different networking layers. So just like in computers, we have different layers where we might have an operating system language and then a high order language and so forth, all the way up to applications at the highest level. You know, what are the losses that occur across layers like that in information network systems that are basically going to be embedded in what we call now neural networks? And then we see 1996 to 1997. IBM's Big Blue computer beat world chess champion Garry Kasparov in both a match and a rematch in a first Turing test. Now, in the match in 1996, Kasparov won 4 of 6 of the games. But what was important was that the computer beat him in 2 of them. The next year, the computer beat him in 4 and he only won 2. So what we see is now the computer is capable of doing some things that it hadn't done before. In 2011, IBM Watson computer beat Ken Jennings and Brad Reuter in Jeopardy as another Turing test. Baidu's Minhwa computer categorized images faster than humans were capable of. And in 2016, IBM's DeepMind AlphaGo program beat Lee Sedol, who is world champion Go player in a 5-match games. Now, this is significant because what we see is here is the computer system is growing better and better. Now, we've created learning environments. So here is artwork created by Vincent van Gogh, a favorite artist of mine, actually. And we start seeing these are 3 of his themes about starry nights. So we have starry nights over the Rhone River in Germany. We have another starry night, and then a road with cypress and star. And these all have these sort of indicative swirling art backgrounds that were typical of Van Gogh's style. Now, when these are fed into a machine learning program today, the machine learning was actually based on pictures of animals. And how do I create then these different things? By turning them inside of themselves, much like fractal experiences do when we're taking a look at geometric shapes, but we're now doing these with biological and natural shapes. So what happened in 2014 is that Google's Deep Green system interpreted Van Gogh's Starry Night and created a new piece of art. And we take a look at this, and when you look at it, you can see it's reflective, very highly reflective, of the Van Gogh style. But if you look carefully at it, it's also got originality in it that comes from other things. We see ducks and we see fish and eyes and animals floating in the sky. And then we see people down below, and the cypress tree became a tower. And we look at the base of the tower and we see there's sort of octopus and cows built into it. And so we see a totally different type of abstraction was created by the computer because it understood what Van Gogh was attempting to do, but it used a very different language, a very different way it had learned to create a totally new structure. So I look at this and I say, by 2014, these computers have actually come to have the capability of surpassing human beings, not only in logical analysis, but also in the idea of creativity. Now, what does that mean? Can this be applied to everything? Well, not yet, but it's on its way. And so the question is, how will we cope with that as it keeps learning? So what did these Turing tests prove? Well, Garry Kasparov versus Big Blue. What we saw was this was 200 million chess moves per second were calculated by Big Blue. So no matter what Kasparov did, Big Blue could figure out what's the highest probability move he'll make next, and then make their move based on logical rules applied to that probability tree. In Turing Test 2, the Jeopardy contest, what we see is IBM Watson is using a different algorithm. It's using pairing question answering artificial intelligence and big data. So it parses out the key terms in the questions, matches it to data sets to find out what is the most appropriate answer. And it returns the highest probability answer. And what we see is that's the type of recognition system that we see that operates when Amazon is making book recommendations based on what you've seen in the past. In the 2016 Go match, we see that this was a 5-game set. But now what's happening is that the deep mind couldn't learn by seeing games of other people. You know, the original Deep Blue learned by studying games played by masters to get its set of rules. But this time, it had to play itself. And so what that means is it's recursive learning, learning that comes by self-learning. And that's because there were 3.5 trillion possible moves available in a Go game. So it's much more complex in terms of the analytic situation. The people who are the masters at this level and who appear in that level have been working on this for many tens of years. But interestingly enough, as this was a match that was originally done in Korea, the IBM DeepMind computer was awarded Dan Level 9, the highest level of a Go master in the world, for the performance that it had in this set of games. Test number 4, novel artwork creation by Google's Deep Dream. So they applied something called conceptualism. And what this is doing is taking the art formats that it's learned from past experiences. So it was originally fed a algorithm set of animals. And it was learning how do you put animals together in different patterns and make them recursive. So if you start looking in, for instance, in the eye of one animal, you start seeing reflected there another animal. And you start peering into that other animal. The next time you see, there's another animal. It's kind of like these Matryoshka dolls in Russia, where you keep finding something hidden inside. And what this Deep Dream did was it created an original piece of art by applying what's called deep learning. So it's searching for meaning of information based on probabilities. So Deep Dream you could consider a visual synthesizer that's categorizing patterns inside of images and enhances them to create this bizarre, dreamlike works of art. Well, the challenge is, what we want to do with artificial intelligence is we would like to actually apply it in productive organizations, manufacturing, service applications, for instance. And what AI does is it uses machine-based applications that can combine hardware and software and signal processing to demonstrate its intelligence. On the other hand, human intelligence describes the natural intelligence of humans or animals that's the result of their observation of their environment, developing their awareness of its opportunities, and making decisions about how to act in ways that will optimize achievement of their own objectives. So Russell and Norvig identified 4 goals in developing AI systems as a way to distinguish and differentiate computer systems from human systems on the basis of how they act. And I like to think of this perhaps in the way of Daniel Kahneman in his book, Thinking Fast and Slow. So in humanistic systems, thinking processes and actions replicate how humans behave. This is what Kahneman called System 1, where we use emotionally based logic. And he said this prevails about 70% of the time that we make as humans decisions. In a computer mechanism, that we see that the mechanisms for thinking and acting are only influenced by the rational structure. And for Kahneman, this was Systems 2 logical structure of applying decision makings without the influence of System 1 emotions. And what we see is this is pure logic. Now, the very first artificial intelligence systems did exactly this. And now what we start seeing is that we can now bring feelings in. And so we start replicating based on what people learn from the human interaction. And then from that, they actually create new learning algorithms about their future. So, you want to do AI? What does it mean? Well, artificial intelligence algorithms are designed to make decisions. So it's divided into 2 distinct categories. It can be called hard AI and soft AI. So when I worked in this field in the 1970s, it was all hard AI. That means we had to hard code the algorithm where the choices in logic path are predetermined to follow a particular prescribed structure. So we figured out the algorithm, we programmed the system to do it, and to use data to follow those pathways as fast as possible. Now, the computers made it happen much faster than we could as humans. But we basically trained the computer to be an expert after learning from experts. Now, soft AI is different. Here we see the algorithms are adaptive and they make their own choices how to branch out in decision trees that are based on associations or interpretations that they themselves derive from the data itself. So it's not trained by the experts. So this is how the computer in the AlphaGo program was able to beat the person, because it trained itself to think. How do I actually move in all of these situations? And then what can I learn? And so it played games against itself, say, well, what was successful and what wasn't successful by applying these particular rules and circumstances. Now, we also see that AI is segmented into 2 other categories. It can be called weak AI versus strong AI. And weak AI, also sometimes called narrow AI, is trained to focus on specific tasks, like the game of chess. Strong AI, though, is also known as superintelligence, or sometimes it's called artificial general intelligence. And it occurs when machines gain self-aware consciousness and has the ability to solve problems, learn, create, and plan in the future in ways that surpass a human brain. This is often what we see, what's happening in terms of the science fiction movies we see. And I remember the precognition AI systems that were actually happening in a Tom Cruise film, where what he was doing is they had these cognition capabilities that said, this is a pre-crime situation, go out and stop it before it happens. So this is the sort of thing, we as human beings can't make that choice. We don't know what's going to happen, but artificial intelligence might be able to. So what AI is doing is it's discovering what we call profound knowledge. And we see there's 3 levels at which the data can be processed. So all of AI exists because we have big data. We can capture data rapidly, we can process it rapidly, we can store it, it's highly accessible, and it's available in long-term histories. So what we want to do in AI is discover what are the patterns that are inherent in that data. So that's basically pattern recognition types of things. And we apply signal processing. Where are the strongest probabilities of association that rely on that data? Now, embedded in AI is called machine learning. And machine learning uses that large data set with some intervention of experts or particularly case studies, for instance, that help train the algorithm to determine what is that inherent probability hierarchy for making those choices. And deep learning is going even a step further. Here what we're doing is the computer is using feature extraction to larger sets, and there is no human intervention. This is what happened when deep learning was going on in the AlphaGo program, because it was teaching itself those things, and it was going beyond just traditional machine learning. So as data is collected, the issue becomes, how do we process it? Do we use it in real time to calculate states, or collect it over time to discover trends? So that's a traditional way to proceed. That's what we've done in the past with statistical process control. However, in the AI approach, learning is engaged in the process, and it's focused on the computer's learning, not on the human learning. So what we see is that we have had in this last decade major advances in artificial intelligence. And it's been characterized as 4 waves of advances. And so we see the first wave is Internet AI. And this is basically around 2010. And here we see searching algorithms where you can go in browsers and look for things. We see computer games where we're playing against a computer or other people in the network. E-commerce is coming out where we can interact and maybe have, suggestions about what you want to buy in these situations. Advertisements in social media, internet lifestyle, all of these came about around 2010, became possibilities. The wave 2 was business AI. And here we start thinking about, how do we deal with money, banks, insurance, finance, trading issues. How do we do education or supply chain management, managing the back office of organizations that are facing customers. It's also came into public service, medical, and logistics. And in 2016, we started seeing perceptron AI. And this is now getting into the fields like security, retail, energy, smart home, smart city. And here we start seeing AI coupled with the Internet of Things. And so we now start having this capability of building, if you will, this linkage between equipment and thinking processes. Wave 4 was actually beginning in 2018. And this is the time that we started envisioning this idea of Quality 4.0. So at that point in time, we had seen the emergence of smart warehouses, manufacturing agriculture as a system, autonomous cars, and robotics. And so what we see is that by 2018, AI had become a mainstream technology that's accessible as electricity and the internet. It is available for everybody to apply and get through access to internet connectivity. So that's a major way for it to go in just a decade. So today we start seeing AI has advanced to smart business systems. So it began with big data, about recognizing that data is the critical asset in the age of AI. And what we want to do is turn data into value. The Smart Engine AI says, here we have core competency to empower business intelligence. So we can start taking a look at marketing trends or selling trends. And the third generation, we're talking about smart business intelligence. So this is AI transformation, where we see processes and decisions are now powered by artificial intelligence. So that's a major set of transformations that happened in the last decade. But you know what? 20 years from now, we're going to start seeing a whole new world. And so what we'll see is that by then, AI learns most of human ability to analyze, abstract, reason via scalable machine learning. We see breakthrough in human AI symbiosis, the cyborgs, if you will. And here we see Tom Cruise actually doing his thing to find out who was actually guilty of this pre-crime situation. And remember how he's having this virtual interface moving back and forth. That's going to be a possibility by then. We also see immersive and augmented, non-intrusive, if you will, augmented reality and virtual reality, where we actually become part of the computer simulation. And today this is actually happening on a smaller scale and in research laboratories, but it will become mainstream in the next 20 years. We also see quantum computing and quantum artificial intelligence, decentralized intelligence, and green blockchain all becoming realities. I was really impressed. In just May of this year, I came to the realization that 3 of the core technologies for quantum computing are now in the real world. So quantum systems, like in MS-DOS, for instance, how you're going to manage the operating system, they exist for quantum computing. The quantum chip was just released in a physical world by Oxford University. They've actually made them. So the computers can actually be made probably in the next couple of years, but certainly by 2041 they'll be made. And the third component was that we've actually demonstrated that quantum systems are much more capable than human systems. And that's because we've switched in quantum computing from processing data to processing probability distributions. Now, I won't go into all of that, but that's the subject for another lecture. But it's important for us to understand because it builds on what we learned in statistical process control. And says we're actually leapfrogging 2 steps forward as we get to quantum computing. And green blockchain is going to be tremendously important because that's going to say, how will we actually manage this environment in the future? Can we actually create climate control mechanisms that work? And one of those things that's actually being worked on right now by an agribusiness that is located in Australia is this idea of a conceptual blockchain where we have different tokens that can be used to actually, instead of trading carbon, we're actually understanding total implications of the system. So we see artificial intelligence, it's come a long way, and it's going to probably go a long way. There are many things it can't do yet, and it probably still won't do them by 2041. But what we have to realize is that today, artificial intelligence is not only real, but it's being applied in our lives. And so now we have to answer Turing's question. Can machines think? And now we have the answer. Yes, they can. And so for us in the quality community, we have to say, what will we do about it? What does that mean for us? How will we live? So we have to learn to think algorithmically. This means that we have to understand the nature of systems is a singularity composed of interconnected threads that are perceived individually, yet in possession of interactions and implications that dynamically shift over time. And we can interpret them not as the individual data streams, but as the probability of future events to come true based on probability processing in predictive analytics. So humans perceive only individual slices of time. That's a static observation. And it's based on our frequency of sampling observations. We may or may not see how the patterns in the systems are evolving dynamically in time. However, let's consider what happens in the Earth, in this biosphere. So heat is trapped in the atmosphere, and it creates its set of conditions, which we call a climate, which we observe in small slices or states that have stasis. In other words, they're stable. It's today, I look out the weather, it's stable, and it's perceivable. I can say it's a good weather today. As Earth captures more greenhouse gas, more heat is captured and not released to space. The heat has to go someplace. That's what entropy is about. And what we observe is that 50% remains captured in the atmosphere, 25% is distributed to both the geosphere and the hydrosphere. So 1/4 is in the Earth, another 1/4 is in the oceans. And we observe the symptoms of this action. We see extreme weather from connectivity between geosphere and hydrosphere. That's creating the weather situations or extreme weather that we see. The melting of the ice masses is also a result. Warming land creates drought that reduces food supply. So all of those are indicators of the change that we see ahead. And so what we see in thinking algorithmically, everything is connected to everything else as an algorithm. And even if we don't understand the linkages, those linkages are there and can be demonstrated in a world where we analyze with probabilities. Well, facts can be computational or associative. And this was the distinction that was originally made by Turing in his 1936 paper, where he says that computational facts are things that can be expressed in a decimal value of numbers. This type of information is subject to noise. It comes from errors in data measurement or errors in collection or in storage where it's compressed and we lose, if you will, decimal places, or in presentation where we present it in simplified ways where we average the raw data or we convert the raw data into a line chart, or even worse, we say, does it meet our criteria, and we make it yellow, red, or green. So what we see is that data of this type is very productive for automated processing because we don't have to simplify the rules. We can let the computer use the raw data to develop probability distributions and think about them differently. Now, the other type of data is associative facts. And these describe non-numerical relationships that exist through logical subgrouping into some discrete taxonomies, or the association of distinct categories or labels of subgroups or established by drawing inferences from frequent use of labels in similar texts. And this is what's happening in a computer learning situation, machine learning. In these cases, biases that exist in humans may be transferred into conclusions that are not socially proper or represent discriminatory conclusions such as racial or economic profiling. So I was reading about a young lady at MIT in the media lab who discovered that because she was black, the computer couldn't see her face on facial recognition. And we start seeing that systems like this that create a lack of detection based on certain physical characteristics, or maybe it's based on certain social or financial characteristics, can lead to discriminatory problems. So just this last April in the European Union, a law was passed to actually hold us accountable for responsible AI. And that means systems that do not impose on human beings' basic rights. So we see that data must be very carefully monitored to ensure that unethical conclusions or recommendations are not drawn by association inferences. And that means we have to protect both the privacy rights as well as cybersecurity, or if you will, the invasive application of computers into our lives that are intent on creating mischief, or even worse, destroying the very principles by which we live. So into this, we have to then understand some of the dynamics of driving systemic change. And we see there are some cultural inhibitors to digital transformation. For instance, an overly cautious management culture, or following business as usual management practices. Or maybe we have gridlock from excessive management initiatives, where management is thinking, we can eat the whole pie and just keep asking people to change. Maybe we see risk-adverse, uninformed, and reluctant executives who don't want to make a choice. Or we have disengaged and unmotivated employees. And maybe there's a loss of focus during execution and implementation, where the direction is changed by people in the middle of the organization who don't quite want to tell the boss they don't agree, but they just then implement their way. We also see that in this process, lean management principles can facilitate that change. So we define value from the perspective of the deliverables that we give to the people who are intended to receive them. We identify the nature and flow of value creation systems. And we create the waste-free flow of value in those systems, establishing pull that drives performance on the demand that comes from those external customers. And then we pursue perfection in performance towards those goals. Now, the hint, it doesn't start with the technology. So Richard Young, a professor in Northwestern University, made this observation. He's a professor of psychology. He made this observation. A productive system is a collection of if-then rules that form an information processing computer simulation model of some cognitive tasks or range of tasks. That includes its digital twin. Now, the digital twin is an interesting concept because when I was working again back in artificial intelligence, we had simulation algorithms. We had simulation languages, and we were creating, if you will, hard AI simulation systems where we would simulate what was going on and then try to take the lessons from that into the real world. And so what we are starting to see is it's going to be, what's going to be novel in this will be how we actually apply simulation. So today we can do online simulation and then check back and forth between a simulation model and the actual real world data to understand what are the noise sources or the errors between the two. In the future, in quantum computing, what's going to happen is they will actually be done simultaneously, and the computer will learn about the differences between them and self-correct the systems without delay. And so that means that the computer really does move into the driver's seat, not just on these cars that are computer-driven. So we see this productive system includes cognitive acts of learning and maturing, changing over time. And this integration of things and people really is characterizing Quality 4.0. And these production systems actually contain 5 elements. So first is the hardware, software, technological production mechanism. So this is the equipment of manufacturing, whether it's injection molding machines or it's a machine that's actually making printed circuit board assemblies, or it's basically some sort of system that does automatic testing at the end of a production line. And so Those things are a combination of hardware and software systems. The second is the human social systems. This happens when we design a productive system. And this is going to be one of those tasks that never goes away. Humans are going to be involved in designing of many of the systems. But what we also see is that smart AI systems can learn how to design. One of the things that enabled those quantum computer chips to be built at Oxford University was an AI application about line placement, because those patterns were so fine, humans couldn't do it. And so the AI machine taught itself, how do I actually lay out those particular semiconductor chips? Not only did it do it better, it also did it much faster. And we start seeing that we also have execution of systems. So how do we actually execute the systems? Who turns them on? Who actually applies them or points them at audiences or feeds them the initial data sets? Typically, this is happening now because we made choices about how we manage strategy in organizations, whether we're talking about going into a market or we're talking about building a new type of product or introducing it for product launch. A third component are the management systems and a knowledge base that performs the operations, which includes not just the hardware knowledge or the knowledge that's now embedded in the internet cloud, but it also includes human skills and the competence that's built in the brains of the individuals who are embedded in that system. The fourth element is data collection, which describes how the system has operated in the past and creates a feedback loop to help us understand what are the control states that we need to use to manage for the future. And finally, it's the cultural values, the style and moral codes, how people working in groups make decisions, how organizations have decided they wish to behave, and what is it that brings them together in a coalescence of an organization to collaborate on common ways of working. Well, quality professionals actually operate as human intelligence systems. So we have learned to think and act as a human intelligence agent by thinking algorithmically. And so quality professionals have developed ways to process data in rule-based structures. So we take a look at individual control charts. We say we have rules that we can apply to them. We also think algorithmically to observe patterns, special causes of variation, if you will, process capability studies to understand what's good or bad from a perspective of a customer based on the data. We can decipher trends, associate observations into sets of rational subgroups. We can conduct diagnostic analyses based on multiple types of data and develop decisions to improve results as an outcome of that processing effort. So the feedback is used to develop control for the process results. So those are exactly the same actions that an integrated AI algorithm will perform in a productive system. Now, the advantage we have is many other professions are less structured than quality professionals. And their way of thinking will have more difficulty in transitioning to this AI way of thinking, which is more radical than their normal ways of thinking or their patterns of thought have been. So AI has an affinity to aid operations in improving quality. And so it's really a commitment in AI to process improvement. A digital twin models performance of operational systems. It enables simulation of variation in performance system inputs as they change and as the levels of resources that are applied gets modified. And so when we take a look at this, we see that in this sort of system, we have a man-machine system. That's a real-world system. It's getting real-world data, and it's got output. We also see we can feed that real-world data into the digital twin, which is a simulation model. And out of that, we get a model estimate of what's going on. And when we compare the real-world result to the basically noise-free simulation model, we can estimate the error in the system. And so this abstract man-machine algorithm that's happening down there in the simulated system allows us to estimate is noise more than expected or less than expected in the system based on the comparison of the real-world data stream to the ideal state. And so when we forward process that, we get a noise vector. When we backward process it, we get how do we correct that noise vector to get back to the original state. And this comparator, that X there, creates this estimation of modeling error. And then the question becomes, what do we do with it? The practical question is, what needs to be corrected? Is it the real world or is it the simulated system? We begin by correcting the simulated system on trained data sets where we know what's going to happen or we know what we want to happen. This provides a training for the system. And so what happens now is we can adjust the weights and the coefficients in the equations. And then when we go back and we get the model verified, the verification is the technical test. This model works the way we want it to. Then we can apply it for the validation of real world and say, okay, once we add people in this and the environment is, how can we actually get the real world so it actually works closer to that expected simulated world? So how do we make this change for the better happen? Well, really we have to consider two perspectives for developing knowledge. And one is the theory of profound knowledge, and the second is the UDSO model for technology integration. What I'm going to do now is transition into talking about these, and then I'm going to present a case study. And the case study hopefully will give you some idea about how all of this comes to bear in decisions you might need to be making in your own organization. So the first question is, what is this theory of profound knowledge? And so what we see is that profound knowledge is a statistical understanding of what real-world behavior is so future states can be predictable with some confidence. It's basically creating a predictive estimate of probabilities based on changes in our observed data. So Deming identified 4 estimates for discovering profound data. So the first was a system. We have to understand the context in which all work is accomplished. The second is knowledge, and it comes from observing work and defining a theory that can be scientifically tested and confirmed. The third is variation. And what we understand is that difference between the theory, the noise-free environment, and the observed environment, that this how the system operates and steering or guiding the system in the future must be based on the study of variation in its historical performance, and then we create rules about what does it actually mean in terms of the practicalities of the output that's produced. And finally, psychology. And this is understanding the human behavior. How do we motivate people? How do we coordinate them to achieve sustainable cooperative work outcomes? So these are the elements that Deming put into his system. And as we take a look at this, we see that some other people have come up with other ideas on what works. So for instance, based on the learning from pursuing the Turing challenge, IBM created what they call an artificial intelligence ladder to define how to create success in an AI system deployment. And the ladder has 5 steps. First, we collect. That means identify data collection and accessibility. Second, we organize. We create business-ready analytics as a foundation. Third, we analyze. So we're building a scalable, trustworthy, AI-enabled system that can actually make the comparisons. And then we're going to infuse this, integrate and optimize AI in a business system framework. And finally, we modernize this. We elevate that AI local application to a cloud for universal application. Now, the weaknesses in the AI ladder of IBM exist in the first 2 steps. So it's about sorting big data and defining what are the critical factors that must be analyzed. Now, HP, Hewlett-Packard, when I was there in the 1980s, developed a PCDA-based model to address these concerns. This model is particularly important for an SME that's requiring only simple AI applications. So it isn't for the much more advanced systems. It's basically saying, in our company, we can only afford a very limited amount of resource. We have to apply it exactly on point to what is the most important things for us to use in this digital technology. Well, this is the model that was developed in HP, and then I modified it in a 1994 book called Business Systems Engineering. And so we have 2 steps in this process. Step 1 is about building daily management. That's standard work. Step 2 is about building strategic management. And what we see is that in the first step, we understand the system. And that's going through applying what's called the SDCA, or Standardized Do Check Act process. That's a fundamental approach in the Japanese daily management system. And then we cycle that learning. So after we've walked the process, we understand it, we've gone and see what's being done, we then can document the system as is. Because what we have to do is we have to make a comparison of this system to past data. So we have to understand, how does the model relate in terms of data to the way the system was operating in the past? And then we have to say, okay, so to create a future for the system, a system future, or design a system future, we have to simplify that model. So we have to eliminate the waste. We have to eliminate losses. We have to eliminate friction. And we have to eliminate the excesses that are in that system because we don't want to automate them. If we automate systems that way, what we're going to do is we're going to make more waste happen faster. That's not a good outcome. And so finally, after we've simplified the system, now we've created a system that's ready to change. And we see what we see is we've gone through a process where we standardize the work and we improve the work. And now we're ready to transform the work. And that happens in the last step, which we call optimize. And optimize is really about automation. So what we have to think about is, what is our capacity to automate? And this is the approach to understand the nature of work, document standard work, and then simplify it so it's ready for automation. So basically what happens in this final step, it's about systemic design, the readiness to automate. And if we don't have a well-known, understood daily management system, we're not really prepared to make the automation happen. So what happens in each of those steps? So in the understand step, what we're doing is we're asking ourselves, what will it take to understand the system? Taiichi Ohno said, go and see for yourself. That's what Genichi Genbutsu means. And so we have to understand, where does the process flow? Where is it constrained? Where is it leading value? Where is it losing value? Can the workers identify the waste and what waste can't they take care of in the process? And after we understand this, then we can do the as-is process design. Then we go into document. And Taiichi Ohno suggests, don't make it a heavy documentation. Just document it first, and then as you start learning from cycles of testing and applying the rules that you think about for new potential improvements, you keep making it better. And it's the cycles of learning that make it better. It's not coming up with the one best way. If we came up with the one best way at the beginning, workers have no motivation to make it better. All of the effort then becomes wasted time, and they see there's no value in my time. So finding better work and giving supervisors an opportunity to develop and encourage workers further. So these production systems then develop sets of rules that define how to decide and work at the control points in a process. So a control point is that place in a process where we can observe data about process performance for some characteristic we care about. And we can also have an adaptive loop that adjusts the process for that factor to keep it in a state of control. Simplification is about what we do in Lean. It's nothing really new. So these first three steps really give us this standardized do, check, act that creates a work discipline in the daily management system. Whereas the fourth step is going to apply PDCA to drive breakthrough improvements. So what we're going to do is we're going to go beyond the budgets that the process has. We're going to bring new technologies to bear that were not in the original systems. And these are going to be management interventions or strategic changes to the process. Many of them will be transformative about the way we look through. And we have to look before we leap. If we haven't done those first three cycles, we're not really prepared for the advanced technology. Our digitization investments may be lost. And we have to remember that in the 1980s, General Motors invested $20 billion in robotics for automated assembly, and they gained nothing in terms of their goal for increased productivity. Now, they learned a lot about production, they learned about quality, but they didn't actually achieve the productivity they had targeted. So what needs to be learned and why? So first, do we capture the right data? And is it able to give us the insights we need for controlling process performance? That's an important question before we go further. Then the flows that occur in the process for people, documents, materials, service, design, planning, how do all of these, how do we evaluate them? So we take a look at the smoothness and the response. So how does it relate to the pulls trigger that says we're initiating performance? And then the presence of process feedback loops and buffers of material or inaccessible information that's stored in a data lake someplace that we can't find. They need to be investigated to understand the rationale for their existence. Do we need the data? Do we need the material? What's the reason for it? So we don't want to just have systems that will continue to encourage bad behavior in process performance. And then we have to take a look at the interactions that occur between people, processes, and information to understand how can data be used to manage process once we automate it at those control points. So the fourth step is to optimize so we can automate. And what optimization is doing is it's changing the nature of improvements from evolutionary or Kaizen approach to a revolutionary breakthrough, or you might call a Hoshin approach. And when HP first developed this model, they were discussing developing a factory of the future, implementing intensive robotization as many other people were in the late 1980s. But the productivity gains that were sought at that time did not actually become a reality. So HP was automating or needing to automate things like the use of automate insertion equipment into printed circuit boards, to take a look at automating things like testing of printed circuit boards, or maybe the placement of odd form components on a printed circuit board. So there were one-point applications of technology rather than creating a whole line where people weren't evident. So the human component in the large-scale production systems where they went for just robotics control was largely ignored because the pursuit was myopic, where people were just trying to replace humans in the system with robots. Now, what's interesting is, at that point in time, in Hewlett-Packard, for instance, that the cost of the people working in the process was less than 8% of the cost of goods sold. And so, really, if you're trying to optimize just to achieve a savings on the 8%, you're actually not really optimizing overall performance. You're sub-optimizing it. And so the UDSO optimize step is really requiring forecasting of technology elements, what's appropriate for our design in the future. It's deciding on the feasibility and cost effective of implementing those technologies and how are they maturing as they come about. And that includes design of the total system, hardware, software, control elements, and the human element. And so the starting point of UDSO is something that is very familiar to many of us in quality. If you don't measure a thing, it's impossible to manage it. I'm sure you've heard that for a long time. But that goes back again a couple thousand years to an old ancient expression in the Orient. And so I can see it in more modern times. It goes back to Sir Francis Bacon, who was understanding what do we mean by this concept of empiricism, or seeing by believing and understanding what's in the data we observe. And it's been stated in a variety of ways over time. Today, more than ever, managing and collecting observations that represent scientific measurements is more important than ever. And it's the foundation upon which an understanding of how to make improvements is founded. All four elements of that profound knowledge paradigm are needed for improving productive systems. So UDSO begins by establishing a base of human knowledge to develop cycles of learning and assure that process wastes are not automated. So what I want to do now is I want to shift. And I want to shift after we've talked about the theory, we've talked about how it works, we've talked about all of these components of both profound knowledge and UDSO as processes. How can we make this work in a real-world environment that may be something that small and medium-sized enterprises can relate to? So I want to share with you a case study of a real-world injection molding improvement. And what we see is this objective is to design a lean production system for high quality and fast feedback. And so the situation is this. Management has just purchased 4 electronic injection molding machines. They have numerical controls and every possible digital sensor they could buy. So the salesman was very happy with the commission. Now, they have 3 different plastics that they have to mold. 2 are clear windows. 6 are different colored A and B combinations. So there were 3 red, 3 blue, 3 green. And then they had 22 gears that were high tolerance internal parts that had to work properly. So those were used to control precise movement in the product. So if I'm taking a look at that, what they did then was they said, one machine is going to be for clear parts. We have to do that because we know if we have clear Lexan, for instance, that if I change productions to other equipment, that we will actually create black specks. And customers don't like black specks in clear windows. So we should dedicate one machine only to the clear Lexan. Another one will manage the color change. Because what we can do is we can actually convert, if we're doing in each mold the A color, B color, we can actually then match them so the colors match within that set. And even though we're going to change the 3 different colors, we can go so that we have different combinations going from dark to light or from light to dark. And then we don't have to then have an inefficient process. But those 2 pieces of molding equipment were basically set aside for that. And so this left them 22 parts to operate in terms of how the other 2 machines will be operated. Now, at this point in time, the average turnaround time for a mold change was 4 hours. So what that says is, if I'm going to do these 22 molds, I'm going to dedicate 88 hours of productive time just to changing molds, not to making anything. And so the then question is, what do we have? Well, management said, hey, we overspent the budget basically. There's only $100,000 left in our investment to manage this problem. So we're constrained. What are you going to do about it? You just can't buy your way out of it. So the task is, how do we use a technology capability that's already been bought to full advantage and achieve the needed productivity? This might sound something familiar. Management bought something without knowing what they were buying. Sometimes we call this a pig in a poke. Okay, so we didn't really think about, is the pig healthy? Is it young enough that it's actually going to be tender meat, or is it so old it's going to be tough? Well, let me give you an idea about what's in a molding piece of equipment. So if we apply this ADSO concept to SMED and 3S for analysis. So we see basically there's 2 different parts in the molding machine. There's the clamping system where we actually are creating, if you will, the part itself. So there's a mold cavity and the part, and we move it together. So we have a heating and a cooling component to that. Then we have molten plastic coming from the injection side. So the screw is forcing liquid plastic or plasticized material that's heated up. It comes in a hopper, or it comes from some source. It's heated up, and then it goes into the part to fill it. So the question becomes, well, what do you change? Do you change the mold? Do you change the injection machine? Do you change the material feeder, the part injector, the recipe manager for how you do this? Do you change the support equipment, the plastic resin itself, or maybe how you do the setup for the mold? So 3 questions. How do we determine the way to use the automation capability we bought? It's clear. If it applies, we should use it. Second question, what should be the rationale to determine what's needed? So just because we bought it doesn't mean it should be used, and doesn't mean that everything that we bought is of equal value. Just think about your mobile phone. You have lots of capability in that mobile phone, but I've never met anybody who's used all of it. As a matter of fact, I have lots of programs on my mobile phone that really bother me and I'd like to just get rid of them. Okay. And the third question is, how much benefit is gained from each increment of change that we make to the equipment? So let's take a look at this. So we want to dissect this using the ADSO model. And then what should be done? So what is the state space of this problem? That's actually AI type of language. So this is a set of possible solutions that are, situations that are available as solutions. We call this a solution space. So it identifies rational subgroups that may be addressed as options for potential action. What are the potential transitions that are allowable for this particular set of state spaces? So these are the possible moves from one state and alternative positions of that state in a single trial or a cycle of action, or from setup to setup, or mold compression to mold compression. So if each state may be characterized as success or failure, then what we've done is we've created what's called a Markov chain of states. If each path in that Markov chain is unique, then the totality of all the paths may be illustrated as a tree diagram, and we can then have transition probabilities for each of the branches so we know what's the most likely outcome to occur. Well, that's exactly how the Watson computer and Deep Blue were actually programming their algorithms when they were playing chess or Go. And then we see also, how can with this state space and transitions be represented? Now, first, we need to fix the physical world. So what can we actually do in the physical world to take a look at this? So when we go through Understand, Simplify, Understand, Document, Simplify, that's actually focusing on what we have today. So what can we do to improve this end-to-end molding process and take advantage of those? So first is we can look at material science. So in material science, we can understand the chemistry of plasticization. So this is what happens when we melt the plastic. And what's the resultant effect on shrink rate? So when we melt the plastic and we put it in, and we get a heated part that goes into the mold, shrink rate is the amount of shrinkage that's in that part once it cools after it comes out of the mold. So is it possible to incorporate rheology testing or testing about this shrink rate to understand melt flow and shrink rate on cooling of the plastic resin? So the mold may also be modified for ease of changeover. So we could use fixed guides on the molding machine to slide the mold into the machine instead of having to bolt it in. We can apply pneumatic tramps. So instead of, if you will, taking the time to torque down every bolt, they just one step and they're clipped by pneumatic pressure. And they secure the mold in the machine. We can also use snap fits for the input and output of the heat and cooling lines in the mold. We can also have a preheating rack. Normally, many of these machines actually will heat the mold in the injection molding machine, but if we put them in hot, then we have to have a rack and a small crane, if you will, that will move them in place. And if we lay out these two injection molding machines so they're opposite directions to each other, we can have one heating rack and one crane servicing both of those molding stations. And then we can integrate these physical changes in a new discipline of lean production. And this is where we applied single-minute exchange of die and quick changeover methods to actually make those changes happen. So automation is actually the final mile in improvement. So the majority of options to prove all of the state-space transitions in this example are physical, they're not AI. So the automated feed of materials from the pre-dryers was already part of the process. They have massive dryers on the side so the material comes in pre-dried. There is no, if you will, excess water in it. So we only are dealing with basically plastic material. So that investment is not required. Investments have to be made in the embedded sensor was actually largely wasted as we did DOEs and said, well, what are these combinations? What difference do they make? And we found out that the driver in the batch-to-batch variation in terms of the resin is the shrink rate of the resin itself. And so if we also take a look, well, maybe control of the ejector pins. So these are the pins that push the part out when the mold opens up. Because we see that the plastic is hot, it can actually get stuck there. So the mold actually has these spring force that pushes the part out. So in this case, then, we could have a single pick-and-place robot. Again, because we've got the molds back and forth, we can use one to service both of the injection machines, as long as we manage the timing between them, which could be done with the AI system. So merging timing allows one robot to control both of these, just as we had one warming rack and one crane to move the parts. And then resin shrink rate can be added as an a priori condition. In other words, before we even begin, every time we get a new batch, we should take a look at what is this shrink rate in the resin batch, measure it in a couple of different places to make sure it's consistent, because there can be variability even within batch, but it's not so much. And then we can use that as a set point for the a priori learning of how will actually that system will operate in terms of barrel temperatures and pressure settings. And then all of that can be managed by the AI systems. So summary of benefits. So what did we actually get out of doing this? So this was achieved, and here's the story. So here are the investments. These are not in today's dollars, they're in some time late, but you can see the relative importance of it. So the cost per mold fixture is $2,000 each. The 22 molds is $44,000. So that means that the mold themselves had to be changed so that they actually fit this. And that was a tedious job. The rheology testing equipment is $12,000. Lab equipment doesn't come cheap. But this allowed us to actually create this testing process and assure batch-to-batch variability is not out of control. It also allows us to do the set points. The injection machine modifications, each of them cost $4,000. Because what we were doing there is we were really changing the way the molds were attached, but really nothing more. And then the mold heating rack offline was $5,000. The simple pick-and-place robot was probably the most expensive piece of equipment, $15,000. And the cost of the manual positioning crane for the molds was $95,000. So we're basically under $100,000. So we got the budget done, okay? Then the second is, what are the benefits? So reduction in part cost. was 6 cents per part for 22 parts at $10,000 a month. And so that came in at $13,200. Well, that wouldn't justify the change. But the reduction in setup time, which is $50 an hour, and we saw that we saved 400 hours in a week at 4 weeks, was actually $80,000. So we see that the investment payback period was actually occurring in less than 4 weeks. Okay, or approximately maybe 4.1 weeks. The benefits due to the process improvement was 90% of the total. The benefits due to process automation was pretty much less than 10%. So the best return on investment from this particular project came from process management, not from the use of automation. I think that's a major lesson learned. Even if we hadn't taken the lessons about how to do these things in the other world, most of the improvement came because we got the cycle time for changeover down. Interesting enough, Taiichi Ohno says, begin your process in making a lean system with 2 tools. One is SMED and the other is the 3S. So we sort, systematize, and sanitize. And that happens every day. So Siri, Sitan, Sisu. That's the 3S system. Siri, Sitan, the beginning of the day to get your plan right. Sisu at the end of the day to get ready for the next day's work. So there are some takeaway lessons learned from this. So there's 4. So we want to take a look at what did we learn from introduction of enterprise research planning systems in the last 30 years. The second is what has been learned from early introduction of robotic technologies for productive systems. The third area we want to talk about is what are some of the mistakes that early adopters in the SME community have learned by jumping into mass digitization and automation craze. And fourth, what can be recommended as a management checklist for making decisions to invest in these technologies and implement them in their productive systems. So first, lessons learned from ERP introductions. Well, many SMEs have introduced ERP systems. And what did they learn? Well, first, they learned map your process, understand your measures, know what you need to analyze, how to analyze the data, and determine what reports are necessary. Then specify master data items before beginning a software project. Assign operational experts to audit software process models and validate them against the original process maps and measurement systems. This is called regression testing in software, where every time you make a software change, you check the new software and say, does it get the same result against the test program as the original software before modification did? And that's how we test to make sure we haven't changed something that shouldn't be changed in a software system. Integrate data collection points with barcode scanners. Assure the ERP system has tracking capability for material movement across the productive system. And produce only those reports that have a legitimate need by management. Those lessons all apply when we're talking about automation. Early robotics. Well, the initial robotics used in a variety of companies, many of them that I've seen, were basically in pick-and-place robots. They're replacing the hands of people, not their heads. And so they said, we can move these things around. So what we want to do is make digital automation strategic, not a skunkworks project. That's not that buy a robot and try it out. Do we really understand what we need robots for, and can we learn from a robot that's a necessary investment? We should avoid this inclination to automate everything. What is the thing that we absolutely need to automate? Where will we get the benefit from it? So automate simple processes first. Don't try to do everything. How do we eat an elephant? One bite at a time. And the same thing should be true with how we automate systems using artificial intelligence. So the key question is, are you automating high precision tasks that workers must repeat frequently, which would lead to creation of human errors? That's a good place to start, because people don't do high precision repeatedly day in, day out. It's something that robots and automated systems are meant to do. So the principle is let the machines do what what human operators consider to be difficult, demeaning, or demanding. Advanced technology can extend this to creative work requiring decision making, but that's not the place to start. Start small and evaluate the reason for each automated device. Does it need to be done? Can it be done more simply? Have the processes been simplified and streamlined before deciding to automate them? Be sure not to automate the production of waste or embed production inefficiency in robotic production equipment. So what's the risk benefit of doing AI? Well, the pros are, well, quality professionals are data savvy. They know how to think in algorithms and use solution sets to solve complex problems. AI methods work best for processing physical data, as in quality characteristics or process performance data. AI algorithms work well in closed loop and continuous flow manufacturing systems. And those AI applications are also relatively mature, which means pretty much ready to implement in many situations. However, the cons of implementing AI is that these systems tend to work as a black box, which is opaque to workers. They can't see how they're operating. And that's unsettling for workers because they don't understand the rationale and they tend not to trust them. So this is why we have to have some sort of parallel operation so people can build confidence in the AI system's capability. AI systems can be costly to implement or rely on having sophisticated ERP systems as a foundation. So many large companies have found that SAP, for instance, actually offers a whole collection or portfolio of artificial intelligence applications that can be modified for use in an SAP environment. However, AI is often very threatened to workers who fear that in the future that machines will take over the world. And I know in one company they were talking about implementing software robotics. And people says, oh, you're going to train the machine to do my job? And there was a major pushback about this. And they actually had to demonstrate what it really meant in terms of doing things people couldn't even do. And so if we start taking a look at this, we can critique some of the digitization efforts. So here are some of the classic mistakes that have been made by SMEs in technology acquisition. So first is failure to design the productive system so it fits with their operational requirements. Do you really need that robot and its capability? So second, we see a lack of internal engineering support, which leads to design and production outsourcing. One company says, oh, we don't understand about this, so we're just going to assign design and building and installation to an external engineering company. And it may be you're buying much more than is necessary. In that one system, they had 3 robots, actually 4 robots in the system, and they didn't need any of them. So the question is, really, are you buying a pig in a poke? Third, purchasing large specialized machining centers when a less sophisticated system satisfies the needs without encouraging overproduction to assure the management investment payback. I was at one small company, and what they did was they invested in one of these $1 million multi-axis computer manufacturing centers. And to keep it busy, what the accounting people says is we have to have a fast machine payback period. And so they kept the machine operating to drive the costs down so that the payback period would happen faster. But what they were doing was they were producing inventory they didn't need to the point where they actually ended up going bankrupt because they had all this inventory of parts. They invested all of their operating capital in that, and they actually didn't have the capability to continue running the business. So it was a bad choice. Next is we should incorporate advanced technology to we should not incorporate, advanced technology to assure managerial bragging rights or marketing positions when the systems don't add value. You know, some people just want to have bragging rights. Oh, we're an AI-enabled company. Look, we're at the leading edge of our industry. You know, I'm ahead of the competition. And if it doesn't add value, it's actually a loss. And then maybe another one is not investing in necessary technology due to fear. You know, do we run away from making investments that we really should be making because we don't have that capability? So how do we apply or adapt new technology? So we have to carefully ration our investments so they support our needs. So first, we have to know our production process and keep the application of automation targeted on simplicity of design. Second, create technology adoption teams that are cross-functional and include non-technologist users to assure adoption of the recommended systems, as well as a pragmatic introduction of them. Third, we have to identify what are the pain points in your production system where this technology will have tangible benefits. So don't get fooled by hot applications or the app of the day or the technology of the day that are just being touted in Fortune magazine or some other place that says this is what you need to have. So don't buy based on, quote, popularity. And then finally, plan carefully the sequence of technology introduction. Pay attention to the needs to have synchronicity in the flow of materials with the flow of the information. The two flows have to be held in a synchronous environment. If they become asynchronous, you're going to have a mess. If these flows become discontinuous, then failure will be a result. So, designing your future will demand creativity. So what I urge you to do is take control of your problem today and innovate appropriately. Yes, this is a role where quality people can move from daily management system into creative design and create a future career for yourselves. So, thank you for your attention.